Here we have four charges, Q1 through Q4, at position vectors R1 through R4. If these were all positive charges, they would all be repelling each other. If you weren't holding them in place, they would accelerate away, gaining kinetic energy. This kinetic energy would come from the potential energy of this charge configuration. Let's determine the potential energy, the energy stored in a charge configuration. If these charges were at infinity, to bring them into these positions would take work. You'd have to apply forces to each charge and move them to their final positions. The amount of work that takes would be the potential energy of this charge configuration. Before developing the equation for the energy in a charge configuration, let's work a specific problem to find the energy in the following charge configuration. By working this problem, we will develop a mental model for why there's energy in this charge configuration before we develop an abstract equation for it. Here is our charge configuration. Let's take the three charges and move them all out to infinity. If the charges are all at infinity, there's no electric field intensity anywhere in space. We are now going to bring the charges in one at a time. So let's first bring Q sub 1 in. The amount of work it takes to bring Q sub 1 in is going to be 0 because at this point there's no electric field intensity anywhere because Q1 is the only charge in space. Now let's bring in Q sub 2. It is going to take work to bring in Q sub 2 because there's an electric field intensity caused by charge Q sub 1. V sub 2(1) is going to be the amount of work to bring 1 coulomb of charge from infinity to the location of Q2 with Q1 present. In a previous video, we found that quantity, and it is Q1 over 4 pi epsilon sub 0 times the distance away our point is, which is 9 meters. So if this is the work to move 1 coulomb to position where Q sub 2 is, the amount of work to move Q2 there is just Q2 times V sub 2(1). So let's put in our values of Q1 and Q2 and epsilon sub 0 and calculate this work. So I've substituted in our values. These meters cancel. 4 pi over 36 pi is 9, and these 9s cancel. 2 times 5 is 10. We have a 10 to the minus 12 over 10 to the minus 9, so that leaves a 10 to the minus 3, and we have coulombs squared over farads. So the work is 10 to the minus 2 joules. Let's look at these units. A farad is a coulomb per volt, which we'll get to later when we talk about capacitors. So this becomes a coulomb times a volt. A volt is a joule per coulomb, so we're left with joules. So the work to bring in the second charge is 10 to the minus 2 joules. Now let's bring in our third charge. There is now the electric field intensity from Q1 and Q2 when we bring in Q3, so it will take work to position charge Q sub 3. V sub 3(1) is the work to bring 1 coulomb from infinity to the position of Q3 if only Q1 were present. We know the equation to determine that work. V sub 3(2) is the work to bring 1 coulomb from infinity to the position of Q3 if just Q2 were present. We know the equation to determine that work. Superposition holds, so V sub 3(1) plus V sub 3(2) is the work to bring 1 coulomb of charge from infinity to the location of Q sub 3. If we multiply V sub 3(1) plus V sub 3(2) by Q sub 3, we have the amount of work it takes to position Q sub 3 if Q1 and Q2 were present. So now let's just substitute in for our charges and epsilon sub 0. Again, the meters cancel. 4 pi over 36 pi is 9. The 9's cancel. The rest of the calculation you can do quickly without a calculator and find the work to position Q3 if Q1 and Q2 were present is 0.07 joules. So the work to position Q1, Q2, and Q3 is the sum of these three works, which is the energy stored in the configuration of our three charges, and that is 8 times 10 to the minus 2 joules. If we start to have more than 3 charges, this process would get cumbersome, so we need to develop an equation for finding the energy stored in a collection of particles. But for problems I'll give you on homework or on an exam, there will only be 2 or 3 charges, so I would recommend that you go through it in this process because it will show you understand the concept, and it's very easy to make an error trying to apply the equation we're about to develop. Here we have 4 charges, and again we're going to bring them in one at a time. Each time we bring in a charge, we'll calculate how much work it took to bring in that charge. We will then sum the work it took to assemble all the charges, and that'll be the energy stored in this charge configuration. The order we'll bring the charges in is Q1, then Q2, then Q3, then Q4. Q1 being the first charge brought in takes no work. It takes work to bring in charge 2 because charge 1 is already here. V sub 2(1) is the amount of work to bring 1 coulomb of charge from infinity to the location of Q2 if Q1 were present. So we multiply that by Q2 to find how much work it took to position Q sub 2. Now we bring in Q3 with Q1 and Q2 present. V sub 3(1) is the amount of work to bring 1 coulomb of charge from infinity to the location of Q3 if just Q1 were present. V sub 3(2) is the amount of work to bring 1 coulomb of charge from infinity to the location of Q3 if just Q2 were present. So the amount of work to bring in Q3 with Q1 and Q2 present is just V sub 3(1) plus V sub 3(2) times Q sub 3. And similarly to find the work to position Q sub 4 if 1, 2, and 3 are already there. Summing these 4 energies, we get the amount of work to position our 4 charges. This is essentially the process we just went through with that specific example, finding how much work was required to assemble those 3 charges. To get a general expression, let's go back and move all 4 charges to infinity, but bring them in the opposite order. When we bring in Q4 first, there's no electric field intensity, so it takes no work to bring in Q sub 4. When we bring in Q3, Q4 is present, so there will be some work. V sub 3(4) is the amount of work to move 1 coulomb of charge from infinity to the location of Q sub 3 if Q sub 4 were present. So Q sub 3 times V sub 3(4) is the amount of work to position Q3 if Q4 were present. And similarly, to find the amount of work to position Q2 if Q4 and Q3 were present. Finally, we position our last charge, Q sub 1. The work to position Q1 is the work to position Q1 if only Q4 were present, plus the work to position Q1 if only Q3 were present, plus the work to position Q1 if only Q2 were present. The sum of these 4 works is the energy stored in this configuration of 4 charges. The work to assemble these four charges doesn't matter the order with which we bring the charges in. So these two works are going to be the same. So let's add these two equations. When we sum these two equations, on the left we'll get twice the amount of work it took to assemble the charges. On the right-hand side, grouping these three terms and factoring out a q sub 2, grouping these three terms and factoring out a q sub 3, factoring out a q sub 1 from these three terms, and factoring out a q sub 4 from these three terms. The sum of these three potentials is just the potential at the location of Q2 due to charges Q1, Q3, and Q4, and let me call that V sub 2. Similarly, the sum of these three potentials is the potential at the location of charge Q3 due to charges Q1, Q2, and Q4, and I'll call that V sub 3. Similarly, for the sum of these three potentials, which will be V sub 1, and these three potentials, which will be V sub 4. So twice the energy in our configuration of charges is equal to the potential at location of Q2 times Q2 plus the potential at the location of Q3 times Q3 plus the potential at the location of Q1 times Q1 plus the potential at the location of Q4 times Q4. So it's simple to see that an extension to n charges would be this equation right here, and now we can solve for W to get our general expression for the energy stored in a configuration of n charges. If instead of point charges we had some volume charge density, then if you take a differential volume, dV, times rho sub v, we would have our differential charge. So for our point charge here, let's substitute in our differential charge, and the summation becomes an integral over the region of your charge distribution.